Today, we're diving into a theory that could completely flip modern physics on its head. It's called the dark energy illusion. You've probably heard about dark energy, right? This mysterious force that supposedly makes up like 70% of our entire universe, pushing everything apart. It's been the bedrock of cosmology for decades. But what if it's all a massive misunderstanding? What if the whole thing is just an illusion? So, where do we even start? Well, our story begins with a brand new clue, a really strange finding from our most advanced map of the universe. And let me tell you, it's got physicists completely stumped. Okay, so this new clue comes from an incredible instrument called DESI. That stands for the Dark Energy Spectroscopic Instrument. And what it's done is just mind-blowing. It's created the most detailed 3D map of the universe ever. We're talking over 14 million galaxies mapped out across 11 billion years of cosmic history. And deep in that data, it found something that suggests dark energy isn't this simple, steady force we always thought it was. All right, so what does this actually mean for everything we think we know about the cosmos? Well, simply put, it's a huge problem. A massive headache for what's called the standard model of cosmology. Let me break down the conflict for you. On one side, we have our current champion theory, the standard model of cosmology, also known as ΛCDM. For years, this model has told us that dark energy is a constant. It never changes. It's just a fundamental, unchanging force of nature. But this new data from DESI, it's saying the complete opposite. It's showing that dark energy's influence might actually be changing over billions of years. And to really get how weird this is, we need to talk about something called the phantom line. Okay, stick with me here. In cosmology, there's this number, they call it W, that basically describes how dark energy behaves. Now, the standard model is super strict about this. It says W has to be exactly -1. Always, no exceptions. Think of it like a cosmic speed limit you just can't break. Everyone thought crossing that line was impossible, unless you started talking about some really bizarre, almost supernatural physics. And here's the kicker. This is where things get really wild. The DSI data isn't just suggesting that dark energy changes, it looks like it's actually crossing that impossible line. This phantom crossing, as they call it, is a direct punch in the face to the standard model. I mean, if this is real, our entire picture of the universe is fundamentally wrong and needs to be thrown out. So what gives? Is our best theory of the universe just broken? Or could there be another way to explain all this? Well, there is. A pretty radical new theory says this is all one big misunderstanding, and it's caused by something called a cosmic standing wave. This new contender is called mode identity theory, or MIT for short, and its core idea is, well, it's stunning. It's proposing that the change we think we're seeing in dark energy, it isn't real. It's all an illusion. Okay, so how on earth could something this fundamental be an illusion? The theory uses this really clever analogy. Just imagine that the true fundamental energy of the universe, the real dark energy, is like a perfectly flat, unchanging seafloor. Now picture a massive, slow-moving wave rolling across the surface of that ocean. If you're in a boat on that wave, your measurements of the depth are going to go up and down, right? But the seafloor itself, the actual reality, never changed. It was the wave that was changing your point of view. And that is exactly what this theory suggests is happening in the cosmos. The real cosmological constant, what physicists call lambda, is totally fixed. It's not changing one bit. But we, the observers, our galaxy, everything, are all riding on a giant cosmic wave. And it's this wave that's modulating our view, making it look like lambda is changing when it really isn't. All right, that's a cool idea, but how does being on a cosmic wave explain away that impossible phantom crossing? Well, here's the elegant part. It turns out the crossing isn't real. It's not happening in the universe. It's a glitch in how we're measuring things. So here's the problem in a nutshell. What MIT predicts is the real signal, this smooth, rolling cosine wave. But our current models, they're too simple. They try to fit everything to a straight line. It's kind of like we're trying to measure a big, beautiful curve using nothing but a short, straight ruler. It's just not the right tool for the job. So yeah, our models are built on the assumption that if dark energy changes, it does so in a simple, straight line. But MIT says, nope, it's a wave. So what happens when you try to force that straight line template onto a curve? The math basically freaks out. It twists and contorts to get the best possible fit it can, and in that process, it creates the illusion that it crossed the phantom line. The crossing was never there. It's a ghost in the machine, an artifact created by our own flawed measurement tool. And this brings us to a really powerful quote from the paper itself. The phantom crossing is not in the expansion history, but in the template used to fit it. Think about that. It's not the universe breaking the laws of physics. It's our own model creating a phantom signal in the data. Okay, this is a really neat story, a beautiful explanation. But is that all it is, a story? Or does this new theory actually fit the evidence better than the old one? Let's find out. Let's put it on trial. All right, let's put these two theories head-to-head with the latest data. We've got the standard model, ΛCDM, and the new theory, MIT. Now, the number you want to look at here is chi squared. You can think of it like a golf score for a scientific theory. The lower the number, the better it matches reality. And look at that. MIT scores an 11.21, which is a noticeably better fit than the standard model's 13.54. And here's the really crucial part. It gets that better score without adding any extra complexity. It uses the exact same number of parameters, or tuning knobs. But really, all of this comparison boils down to one single critical number, -2.1. So what is this number? It's called the delta AIC score. It's a way statisticians compare models. It's really smart. It rewards a theory for fitting the data well, but it penalizes it for being too complicated. A negative score means the new model is better. And a score of -2.1, that means the data shows a positive preference for MIT over the standard model. So it's not just a different story, it's a statistically better story. And it manages that with zero added complexity. That's a big deal. So, case closed, right? MIT wins? Well, not so fast. In science, a good theory doesn't just explain the data you already have. It has to make bold, testable predictions about the future. And that's exactly what MIT has done. It's really put its neck on the line. The theorists behind this have actually made very specific falsifiable predictions and published them ahead of time. They've predicted the exact shape of this cosmic wave and even where its center should be. But the biggest prediction of all is that the true dark energy density, the seafloor in our analogy, is constant. And we're going to find out soon. New telescopes, like the Euclid Space Telescope, are going to put these predictions to the ultimate test. And if that new data doesn't match up, well, the theory's wrong. Simple as that. That's the beauty of science. And this just leaves us with a really profound final thought. For decades, we have been searching for some kind of exotic, brand new physics to explain why dark energy seems to be changing. But what if? What if we've been looking in completely the wrong direction? This new theory suggests that maybe the great cosmic mystery isn't some flaw in the universe, but a flaw in our own perspective. What if, as the paper says, what evolves is not lambda, but our own point of view?